Chapter 14, Quantum Mechanical Postulates. Section 14.5, Quantum Mechanical Postulate 5. Postulate 5 states that the wave function of a system evolves over time as dictated by the time-dependent Schrodinger equation. H psi equals IH bar delta psi over delta t. H is the Hamiltonian operator. It's the sum of the kinetic energy operator and potential energy operator. Therefore, the physical meaning of H is the total energy of the system. Psi is the wave function. I is the square root of -1. H bar is the reduced Planck constant. H bar equals H over 2 pi. Delta psi over delta t is the first derivative of the wave function psi with respect to time. H bar is roughly 10 to the power of -34 joule second. For a one-dimensional particle, we can write psi as a function of x and t. X is the position, t denotes time. And then the Hamiltonian is simply the kinetic energy in the x direction plus the potential energy as a function of position and time. Again, negative h bar squared over 2m times the second derivative energy operator. Second derivative operator is the kinetic energy operator. And V is the potential energy operator. And H is the total energy operator. So we're going to write out this time-dependent Schrodinger equation right here. H psi is IH bar delta psi over delta t. And H is the kinetic energy operator plus the potential energy operator. We can apply the kinetic energy operator to psi, we get this. We'll apply the potential energy operator to psi, we get this. And then we have a time-dependent Schrodinger equation for a one-dimensional particle. There are two variables, position x, time t. Again, for a one-dimensional particle, its wave function is a function of two variables, the position of the particle x and time t. Now we write out the time-dependent Schrodinger equation. We'll apply the kinetic energy operator to psi. We apply the potential energy operator to psi. This is simply the product of the potential energy function and the wave function. Well, on the left hand side we have H psi, the Hamiltonian operator being applied to psi. On the right hand side we have IH bar times delta psi over delta t. This psi is a function of x and t. Now let's simplify this. This is for time-dependent Schrodinger equation. But what if this term, this potential energy, does not change with time? It's possible for a system to have a potential energy that never changes with time. In that case, V of x and t is simply V of x if this V does not change with time. And then we can separate the spatial coordinate x from the temporal coordinate x as follows. We will make a guess of the form of the wave function psi. We're going to take a guess. We say, well, this psi of x and t might be written as the product of a function of x and a function of t. So we have the lowercase psi of x and f of t, where f of t is a exponential function, e to the power of -i et over h bar. E is the energy of the system, t is time, h bar is the reduced constant. Now let's verify this. If our guess makes sense, we need to apply this IH bar delta over delta t to psi. So it's this side. Now we express the uppercase psi as the product of the lowercase psi of variable x and then a function of t. So we're going to do this, and then we're trying to take the first derivative of psi of x and f of t. So over here, and just because psi of x is independent of time, we can take this out of this derivative operation. So we have IH bar psi of x and then delta over delta t operator being applied to this f of t. F of t is e to the power of negative iet over h bar. It's easy to take the derivative of an exponential function. We just copy the exponential coefficients here, and that's it. And over here we have this exponential function. And now let's simplify this expression. We have I multiplied by negative I. That's just 1. We have h bar cancels h bar. And then in the end we have e. So from here, e times this lowercase psi times f. This f of t is this exponential function. Alright, so this equation, the time-dependent Schrodinger equation, now becomes this. On the left-hand side, we have the kinetic energy being applied to the uppercase psi. This potential energy multiplied by uppercase psi. On the right-hand side, we have this. We have IH bar delta uppercase psi over delta t, which is the energy of the system times the lowercase psi of x only and a function of t. So right here, left equals right. And if we look at this carefully, we notice that we have f of t, f of t, f of t. We're going to just cancel all those. We get this equation. In this equation, there's no longer time. There's only one variable x, the spatial coordinate of this wave function. We have the kinetic energy operator being applied to the lowercase psi, potential energy operator being applied to psi, and the sum is equal to E multiplied by psi. And over here, this also makes sense. Really, it's just the Hamiltonian being applied to psi is equal to E psi. And the physical meaning of the Hamiltonian is the total energy. And this equation does not contain the temporal coordinate t, the temporal variable t. There's no time in this equation, and therefore we call this equation the time-independent equation. It's a time-independent Schrodinger equation. For a one-dimensional particle, when the potential energy operator is independent of time, somehow we can separate the time variable from the spatial variable. We get this time-independent Schrodinger equation. This can be simplified as h psi equals E psi. On the right-hand side, this is just E psi. Psi is a function of x. On the left-hand side, we have the kinetic energy operator applied to psi and potential energy operator applied to psi. The sum of kinetic energy and potential energy operators is simply the Hamiltonian h. And over here, this h does not contain time either. So h here is a time-independent Hamiltonian. H is the sum of kinetic energy and potential energy. Kinetic energy operator here, potential energy operator here. And this lowercase psi is an eigenfunction of the Hamiltonian. E is the corresponding eigenvalue. The physical meaning of H again is the total energy of the one-dimensional system. Because in this H we do not see the temporal variable t. That means this H does not depend on t. That means H is independent of time, and therefore the total energy of the system is also independent of time. The energy remains constant. For a two-dimensional system, the kinetic energy operator is a little bit more complicated. There are two terms, one for the x dimension, one for the y dimension. And the second derivative is simply the first derivative and then the first derivative, just twice. You apply the first derivative twice, and when you do that, you need to hold y constant. When you take the second derivative of psi with respect to y, you need to make sure x is held constant when you do the derivation. And again, the second derivative is simply the first derivative of the first derivative. For a two-dimensional system, the time-independent potential energy operator is denoted by V of x and y. Sometimes we put a caret on top to indicate it's an operator, but usually for potential energy, the operation is simply multiplication. So occasionally we just do not put the caret on top just for simplicity. For a three-dimensional particle, we have x, y, and z, and then time. But then the time-dependent Schrodinger equation can be really complex, because if you look at the kinetic energy operator, we have three different derivatives with respect to x, y, and z. And over here we have a potential energy that depends on x, y, z, and time. And over here, this is simpler. It's still IH bar delta psi over delta t. Again, this psi is a function of x, y, z, and time. But again, if the potential energy V does not change over time, things get simpler. This V now becomes a function of only the spatial coordinates x, y, and z. It does not depend on time. Now we separate the spatial coordinates from time. So we can write out this uppercase psi as the product of two functions. One is the function of x, y, and z. The other is a function of time. The function of time has to be e to the power of negative I e t over h bar for convenience. Now let's evaluate delta psi over delta t. We'll evaluate this because the lowercase psi is independent of time. We can take it out. And now, how do we take the first derivative of exponential function? It's easy. It's negative IE over h bar multiplied by this exponential function. We clean up everything, we get this. It's negative IE over h bar multiplied by the uppercase psi. And therefore, the time-dependent Schrodinger equation becomes this. On the left-hand side, we have the kinetic energy operator being applied to this psi times f. This psi is a function of x, y, and z. F is a function of t. Similarly, we have the potential energy, which does not depend on time, multiplied by psi of x, y, z, multiplied by a function of t. On the right-hand side, we have just the total energy multiplied by the wave function of the system. Now both sides divided by the function of t. ft, 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 they all cancel. Now we have this. We have the kinetic energy operator being applied to the lowercase psi plus v times the lowercase psi equals e times the lowercase psi. Simply put, we have h psi equals e psi. This is the so-called time-independent Schrodinger equation, and this h is time-independent Hamiltonian operator. This h is the sum of the kinetic energy operator plus the potential energy operator. If we have multiple particles, the wave function psi now becomes a function of the positions of all particles and also time. So we have 3m plus 1 variables. H is, well, the kinetic energy operator plus the potential energy operator. The kinetic energy operator is the sum of all kinetic energy operators of all particles. And now we have this time-dependent Schrodinger equation. H psi equals IH bar delta psi over delta t. Again, if the potential energy does not change over time, this V is dependent on the positions of the particles only, then we can get the time-independent Schrodinger equation. H psi equals E psi. Over here, we use the lowercase psi as a function of the positions only. And this H becomes a time-independent Hamiltonian. This H can be expressed as the sum of the kinetic energy operator and the potential energy operator. We do not see any operator that contains time t. Therefore, h is independent of t, and because of that, when we see h psi equals e psi and h does not depend on t, then e does not depend on t. Now this lowercase psi is a function of the positions of all particles. It's a time independent wave function. If the potential energy V does change over time, we can express psi as the sum of Ci psi I. It gets a little complicated. Ci is a coefficient of psi I, but this coefficient may change with time. That means the probability associated with psi sub I may change with time. That corresponds to the change of the, for example, electronic structure in an atom or in a molecule. If we're using this to describe the electrons in a atom or molecule, again, psi sub I is the eigenfunction, the ith eigenfunction of a complete basis set. So what does this mean, a complete basis set? Well, that's just simply the eigenfunctions of this h over here. So if we can solve this time-independent Schrodinger equation, we can get a bunch of eigenfunctions, usually an infinite number of eigenfunctions. And the infinite number of eigenfunctions can form a complete basis set. That means any smooth function can be expressed as a linear combination of the eigenfunctions from this complete basis set. And then we can actually solve this time-dependent Schrodinger equation, h psi equals I h bar delta psi over delta t, and solving this is equivalent to finding how the coefficients c sub I changes with time. So over here we have c sub I here. We're going to just see how the probability of a system in the ith eigenstate changes with time.